Hey friends, welcome to part 3 of this 3-part video series on electrical. Part 1, we went over voltage, potential difference. Part 2, we went over resistance, ohms. And part 3, we're going to be focusing on current, checking amp draw of loads. Things that turn on like compressors, condenser fan motors, anything that is a load. And yes, we're going to be using a meter without test leads. So today you're going to see how with the meter, we're going to be using the clamp function. The clamp function of the meter. And you're going to see how going to both the schematics and the actual unit where we have to actually clamp on it to read amps or current. All right, so before we go into the unit and check amp draw, I highlighted the areas where we're going to be checking for current. So we're going to be checking the outdoor fan motor, your compressor, the ECM, indoor fan, your contactor coil. So you notice, right? These are high voltage components. This is a low voltage component or low voltage load. And these are high voltage loads. But you can still check amp draw regardless of the voltage, as long as it is a live circuit. We can even check the transformer too, right? Because the transformer is a load as well, right? We're going from high voltage into 208 to 24 volts. That's a load. But we'll keep it to these four for today. And I'll show you a little tip as to what you can do by checking the leg or the line coming from power from the disconnect. And by checking one, it kind of adds up all the components currents that are on, and you're able to check it by just checking one of these legs. So that's a nice way of doing it instead of going to each one and adding them up. But let's go ahead and just go and get a clear explanation, because before we move forward, we need to understand a couple of things. Okay, so right here, amps, alternating current. So the way you check for amp draw is you have to have a meter that has you see that? AAC, amps alternating current. And on this one, you actually have to go to that setting and you actually have to press select, and then it shows up on top. Some meters are automatic, but this one you actually have to press select. But you're either going to see it like this, AAC, amps alternating current, or on your meter it might just say A with a little squiggly line. And the idea is that you're going to check amp draw on just one wire. You're not going to put two wires. You're going to put one wire, which I'll show you right now on the unit. But if you put two, it cancels out. You got to put it around one. And this clamp, it's already made and built because, you don't have to understand like, well, how is it doing that? It already is measuring the magnetic field. Because the point is, when you have current going back and forth, 60 times a second, just like this example, right? You have current going back and forth 60 times a second. It creates this magnetic field. Boom, like this. You'll see this magnetic field. And that magnetic field can make things turn on, pump, in the case of the compressor. The blower motor, make the shaft spin, right? So by having that magnetic field, because it's going 60 times a second, magnetic field, right? And imagine you have a magnetic field going around this wire here. The clamp is going to measure that in the form of current, okay? So the principle here, though, this is important to understand. Whatever you're trying to measure current, it needs to be on. It needs to be on. I cannot emphasize that enough. It needs to be on. And so, of course, more current, more work is being done. Less current, less work is being done. But have in mind, though, you might have a load like a compressor that's going to pull a lot of current. But when you compare that to a condenser fan motor, it's going to pull a lot less current. So just because it's putting less current, it doesn't necessarily mean that something's wrong with it. It's just not doing a lot of work. Now, of course, if a compressor is putting a lot less current than usual, then that can tell you there's something else going on. And these are some of the terms that you kind of want to have in mind. Rated load amps, RLA, full load amps, and then LRA, locked rotor amps. So back in the day, compressors would use full load amps and locked rotor amps. So this hasn't changed, and I'll show you an example of that. But compressors, I think before 1976, I forgot the year, they would use full load amps on compressors. But all the compressors that you see today, they use rated load amps, okay? So for the compressor that we're gonna check, we're gonna be checking RLA, rated load amps, and then we're gonna check the locked rotor amps. The full load amps, you will see that in the case that, in this case right here, the condenser fan motor, they don't have RLA. It's full load amps, okay? And there's, of course, there's a reason why they use full load amps on the condenser fan motors and not on the compressor. There's the science behind that. But today I'm just gonna show you how to check amp draw. Just know that in compressors, you'll see RLA. In condenser fan motors and other motors, you'll see FLA for the most part, okay? But like I said, when it's less current than usual in the case of the compressor, which I'm going to show you in a bit, that tells you, hey, it could be low on charge. It could be overcharged because it's pulling too much current. Maybe it has a dirty condenser. And this is where I got confused for a second when I started off in the field. But when you're dealing with permanent split capacitor motors, right? Your compressor, your condenser fan, motors that take a capacitor, you're gonna check and put your meter, right? Your meter and check amp draw on your common. If you remember, compressors, condenser fan motors, they have a run winding and a start winding. Run winding and start winding. But the thing that they share in common is your common. So you're gonna check your common for amp draw. That's gonna give you the true number for your amp draw. So if you're dealing with the PSC indoor motor that's 120 volts, then you would check your neutral, right? Not so much your speed, but you would check your neutral. All right, so now we're gonna go to the unit, and then I'm gonna show you all the examples of different loads and the current. You're gonna see how I can manipulate the compressor so it can change the current, and that can give you an idea, because that basically is a symptom of something possibly not working correctly. So first things first though, we gotta make sure there's power, and then we can measure current. So let's go ahead and check the amp draw of this contactor coil. So normally this is how it would be wired. You have what is your common, right? Your common, and then your 24 volts, your action, your Y coming from your thermostat essentially. So right now, if you look at it carefully, it's not being pushed in. And if I were to check 24 volts, there's no 24 volts present. So obviously my current would be 0. It would be 0. And I can confirm that, right? If I go ahead and get my meter, put it on AAC, amp draw, I'm gonna go ahead and put it around the common, okay? And let's go ahead and just kind of get situated so you can see 0, okay? So this is what I want you to pay attention to though, right? My wire is gonna stay there. Once I energize that contactor coil, right? I actually have 24 volts right here present with me. So I got 24 volts right here. Once I energize that and that gets pushed in, you're gonna see that change, because now there's current going back and forth. Remember, I need 3 things for a circuit. I need a potential difference, which is my 24 volts. I need a load, which is my contactor coil. And I need a path for the current to travel, which is my wire. But it's traveling back and forth because of that potential of the 24 volts, right? It's going like this, 60 times a second, boom. And just imagine little balls, like on a seesaw, just going like this, flowing back and forth. So I'm gonna go ahead and power it up. Keep an eye on that. I'm gonna send 24 volts right now. Okay, look at that. It's pulling 0.37. So it is less than 1 amp, but it's pulling current. And look at that, that switch there, the little push button, that's pushed in. But to confirm, I know that I'm pulling amps. I'm checking my current on one wire, brown. On this one, on the common. But look, now it's 0.5, so that's how much current it's pulling right now. But you see, you can check and confirm that it is pulling current even on a low voltage component like the contactor coil. Okay, so now we're gonna check the indoor motor, the ECM. So if you were to look at that carefully there, you have this connector right there, okay? Right there. So the top 5 are low voltage. These are my speed taps. If I were to put that out of the way, you see the bottom ones now. My black and my yellow are my 208. That's high voltage. The green one here is my ground, and my brown one is my common 24 volts. So right now my ECM motor, it has 208 volts present. But what actually gets the motor to turn on is when one of the speed taps receives 24 volts. So what I'm gonna do, and like you said, like I had mentioned earlier, you usually check it on the common, which tends to be black. And the ECM motor example though, with this one, it doesn't really matter because of the way it's wired, but we'll just take it black, put it on the black just to keep it simple. So I'm gonna go ahead and put it on amp draw, right? And I'm gonna go ahead and get the black wire that I had mentioned. This black wire, just put it around 1, okay? And look, I have zero amps. There's nothing going on. Okay, so now I'm gonna go ahead and I'm gonna locate the wire. So this wire here goes to that black 24 volt speed tap. So I have raw 24 volts right here. And I have a video on ECM, so feel free to go to my channel to check it out on how to diagnose them. But you see 0 amps. So once I send 24 volts to that speed tap, the 24 volts part of it is gonna turn on and you're gonna see I'm gonna get some amps. Okay, give it a second. Right there, you see? 1 point, so it's pulling about 1.8 amps, 1.9. So it's doing some work and I can feel some of the air, right, pulling in. But this number here, right, that ECM motor, it has that full load amps and what it should be pulling. So let's say just an example, right? Let's say it's supposed to be pulling 5 amps, okay? And let's say it's pulling 2, and let's say you're calling for cooling. If it's pulling 2 when it should be pulling close to 5, that tells you, hey, there is an issue. Do I have a full-on restriction? What is going on? That if you know, with my motor, right? Because it works on air. If I can suck, I can blow air out. If I can blow air out, I can suck air in. So then by you checking the amp draw, that's another way you can do to check how well that motor is operating, right? Because if it's in the high speed, it should be pulling a lot more amps, or at least close to that full load amps. So obviously this panel right here is open, and it's you know, you get the point, right? It's not gonna be pulling what it should be, but it's pulling close to 2. But you see, I just wanted you to see, now that it's on, we're getting amp draw. And then once I disconnect the 24 volts, it's gonna go to 0 because there's no current going to. It's not on. And if it's not on, no current. No current, no work. Okay, now we're gonna check the condenser fan motor. So if you're able to watch the video on resistance, on that video, I was able to trace out the 3 wires that go to my condenser fan motor, which is this yellow one, this black one, and this brown one. And I was able to specifically point out that my black one here was my common, right? Remember, PSC motors have 2 windings, run winding and start winding, and the wire that they share in common is your common. So that's the one you want to check it on. So in this case, I just gotta make sure which is my my wire here, and it is gonna be, and this is where you would have to confirm, because you see you got another black wire, but it's gonna be this black one back here. Okay, so let's go ahead and put it there. Okay, obviously it's gonna be 0. You see, it's 0. Why is it 0? Because it's not on. Okay, that's it. It needs to be on, right? It needs to be on so that I can be pulling current. Okay, or at least measure it, right? I need to be able to measure current, but it's got to be on. So let's go ahead and do that. So for this example, I did disconnect the plug. This is going to be for the compressor. This is going to be the one we're going to do next. But with this specific condenser fan motor, let's see if we're able to see it. You might not, and if not, that's okay. I can check it out for you. But let's see. Right there. Let's see how much what the full load amps is. Ooh, let's see. Oh, it's right there. Full load amps. You see 0.64 /0.71. So it should be around there, right? But it's 0.64. So full load amps, 0.64. And I think the reason why it gives us 2 different amp draws is because it can take 208 or 230. So since we're powering it up with 208, it should be 0.64 or close to it. Okay, so Remember that number, 0.64, okay? So 0.64. So now let's go ahead and turn on the condenser fan, right? And then let's see how much we're pulling. So I'm gonna do the same thing I did earlier, but I'm gonna get straight 24 volts, and I'm just gonna power up that contactor because the power for the condenser is coming from essentially from the contactor here. So let's go ahead and okay. Let's give it a second. Okay, you see, it did kind of go up, but then it came down to 0.6. There you go, 0.64. It's pulling right under the full load amps, right? Full load amps. It told me up there 0.64, and look at that, 0.63, 0.64. Awesome. And I'm checking it on the common. Now this is good for troubleshooting because of this reason. Look what I'm gonna do. That number there is gonna change once I do this. I'm gonna go ahead and get this mat that I had ready, okay? Okay, so let's say you have a dirty condenser. Let's say you have a dirty condenser, right? 0.64, it's good. But let's say you have a dirty condenser, okay? So let's go ahead and put this over that, okay? All right. Dirty condenser, it's not too much of a restriction. It is pretty bad, but air is still coming out, but there's a restriction. Look at that right there. It went from 0.64 to 0.73. I gained basically 0.10 more. So it's trying to do its job. Now I'm just wasting energy because I didn't clean my condenser, right? And now to try to make up for the same amount of work that it's intended to, now it's got to put more energy because it's a dirty condenser. So you see, that amp draw can fluctuate. That is why you want to make sure the condenser is clean. And the way that this condenser fan works is under the concept of the way it is built. They call it a propeller fan, an axial fan. But right now it's trying to work harder. So it's actually spinning a little bit faster, doing more work to try to reject heat. But now if I take that out, it's going to return to 0.64 because it doesn't have that restriction. Now it can breathe, it can suck the air in through here and push it out through there. So as you can see, by checking amp draw, it can give you a symptom. Of course, find out what the full load amps is, put it on the right wire. By checking that amp draw though, it can tell you what is going on with the condenser fan motor. We always want to be around that full load amp. And that's just another way to troubleshoot and diagnose how well that motor is working. All right, so now let's check the current, the amp draw of the compressor. So there's a couple of things we want to keep in mind. We want to kind of write down on the side. So let's see if we can see that there. You see locked rotor amps, 59. You see that right there, 59.5, and then operating max, it says 14. So I kind of wrote that down right here, right? So this is my rated load amps. Of course, it didn't say that, but it's telling you how much it should be pulling, 14 amps. And then when the compressor gets stuck and it's not pumping, right, the rotor is locked, it pulls, it should be pulling close to 59.5, okay? But this number here, right, this is the number we're going to be focusing on today. And I'll show you an example of locked rotor amps as well. But that's what we should be pulling. Now, have in mind though, okay, this is important. It does say it's 14. But that 14 can change due to a lot of things, okay? If you have a dirty filter, if you have a dirty condenser, if you're undercharged, if you're overcharged, guess what? If you're overcharged, that compressor is pumping more, is doing more work, and guess what's gonna happen to that current? It's gonna go up. And if it exceeds that 14, that's not good because it's telling you it should be at 14. And even under heavy load, and if everything is clean, good airflow, it'll be close to 14. And even if you're not that close to 14, it should be somewhere around that ballpark. But let's say now it's low on charge and you're pulling 4 amps or 5 amps. You're not doing a lot of work, right? And so by just checking amp draw from a compressor, besides checking superheat and your charge, there's another way to find out what's going on with the compressor by checking just the amp draw. getting the operating max, getting the rated load amps, and it's telling you it should be around here. And if it's not even close to that number, something is going on. And you're gonna see how I get to fluctuate that number due to some of the scenarios I'm gonna be creating. So we already got running load amps, rated load amps rather. In this case, they have it as operating max. And just one quick thing, I know that it's amperage because on the Ohm's law table, that I refers to your current, your amp draw. But so these are the numbers, right? Just to kind of have in mind. So now I'm gonna turn it on, but of course before that, we have our meter, we gotta put it on amp draw, and we gotta look for common, right? So we got, what do we got there? We got blue, yellow, and black. Black is my common, okay, and it also says it right here, black is common. So right now, obviously it's not on, you see, it's 0. So now let's go ahead and call for cooling, okay? Let's call for cooling. Let me go ahead and turn it on. Okay, and it's a heat pump, so I gotta send 24 volts to my reversing valve, and then let me send 24 volts to that contactor. Okay, so you see it turned on. You might not be able to hear it on your end, but I know you know it's on because it's pulling amps. Okay, so we'll just keep an eye on that right there. 4.5, and so yeah, you're supposed to wait a little bit, right? You're supposed to wait 10 minutes so the compressor can pump and do its thing. So it's pulling 4.58. The condenser fan has turned on. Okay, so of course, whenever you check your compressor, airflow has to be good. So I have to close this. If not, it's gonna give me some weird numbers. Okay, so now let's go back. Let's see what we're getting now. 4.8. So we're actually not pulling. We are not pulling a lot of amps. Now have in mind though, right? I think this system might be undercharged, but this is the point here though. Look at the surroundings, at least right now in the lab where I'm at. It's kind of cold right now. You call for cooling when it's hot. So even if it's properly charged and you're calling for cooling though on a cold day, it's not under load. The compressor needs heat so that it can do its thing with the refrigeration cycle. But if it's cold, it's gonna throw it off, and you're gonna be like, oh, it's low on charge because it's low amps. No, it's not. It's just not under it's not under load, right? And it's heat to do its thing. So right now it's pulling 4.7, and it's working, right? It turned on, and it could be undercharged, right? And if it was overcharged, it would be pulling more than 14, right? This is what I want you to see though. So look at where I'm at right now. I'm at 4.8, right? Close to 4.8. Look at that number change when I do this. I'm gonna go ahead and introduce a dirty condenser scenario. Okay, let's go ahead and, okay, dirty condenser, okay? All right, so that's blocked off. It was at 4.8, right? 4.8. You see, now I'm at 5.1 because now I had more heat collected in the refrigeration system. My head pressure goes up, my compression ratio goes up, it's pumping more, working harder, and you see, now you're just wasting energy. But that's what I wanted you to see though. By me having a dirty condenser, right? In the case of in this compressor, you see, I'm already up almost half of 1 amp. It went from 4.8 to 5.6. It's almost 1 amp over. So that's what I'm trying to get. I guess the point I'm trying to get across. If you have a dirty condenser, right? Dirty condenser, you don't have good airflow. If it's overcharged, if it's undercharged, that could impact the 14, right? The 14. So when the system is properly charged, all the airflow is good, you're calling for cooling when it's kind of hot, it's gonna be pulling close to that 14. But right now, because I have a dirty condenser, right, it's pulling, what is that? 5.7, right? So look, now once I get rid of this obstruction, now it can breathe, it can do its job. It's not gonna have a high head pressure. Look at that climb down. You see, it's climbing down. So yes, compressor amperage can fluctuate based on what's going on with the system, right? A lot of factors can happen. That is why cleaning keeping the condenser coil clean, the filters, making sure it's properly charged, all those things play effect in how much current that compressor is gonna be drawing. Another thing you can do with the compressor, that locked rotor amps, that happens when you have a weak cap or you lost all your microfarad reading for your Herm side, right? But look, when the system is operating right, and I'm gonna go ahead and put it so you guys can see. Look at this right here. So this one here, this meter is on your start winding. This one here is on my run winding, okay? So start and run. Okay, remember we have 2 windings. Let me go ahead and call for cooling and look at what's gonna happen. So start and run, okay? So let me go ahead and call the, okay? You see that right there? My start is pulling about 3.68 and then 3.9, okay? So right now, both windings are working, right? It's doing its work. Now, of course, like I said, when you check for amp draw, you gotta put it on the common. But I wanna show you one quick thing though, okay? So right now we know it's on, great. They're both pulling. So look at what happens when I do this. And let me go ahead and turn off because I'm gonna be messing with the contactor. Remember with single PSC, permanent split capacitor motors, you need a capacitor. You need a capacitor to create that 90-degree phase shift. So I'm gonna go ahead and power's off, right? So don't think I'm doing this with power. But I remove the Herm. This is the power going to my start winding. And so now that I removed it, okay, I want you to see what's going on with those numbers now, okay? And it's gonna happen pretty fast, so you have to keep an eye on it, right? So let's see if I can do this, maybe like this. Start winding, run winding, okay? Start winding, run winding. Look at what happens to this one here, okay? And you remember that number, right? You remember that number? 59.5 when the compressor locks, okay? So I want you to keep an eye on that number. So locked rotor amps, and then, this is start winding and my run winding. And look at this number here. So I'm gonna go ahead and connect it. Okay. You see, 54. There's nothing going on with the start winding because I removed the Herm wire. You see, and now it went off of the thermal overload. But you saw how much it was pulling? 51, 53, close to that 59.5. So the engineers, they're already in the lab somewhere, they already said, hey, when that capacitor is weak or it doesn't have a good microfarad reading, the most that this compressor is going to pull is that locked rotor amps that they put on the plate, which will be 59.5. But right now, as you were able to see, it pulled close to 53, 54, and that's pretty high. That current, it doesn't know what to do with it, right? Because the start winding, it had no capacitor. So that heat is just being collected and there's a little safety inside the compressor and it opens. So let's see if it does it again. So there we go. There we go, 52, 51. That's a lot of amps and boom, because it opened. So I just wanted to show you that little trick, right? That's what locked rotor amps is. The compressor is locked. It can't move because there's no capacitor. It's pulling all that amp and it doesn't know what to do with it. So instead of it becoming a, an inductance, a load, now it just becomes a resistive heater. It basically becomes a heater. The heat just it just stays there. But when it's working with the start winding, you can make it work, and then that current drops because now it's working. One last thing with the compressor, there's something called saturated or inrush current. So you're able to see how healthy the compressor is. Now, I haven't checked the capacitor, but if I recall, last time we checked it, which was recent, it was okay. I had a chance to check it today, but that capacitor is within working condition. So it's a good cap, okay? So remember that locked rotor amp, 59.5? When the compressor turns on, the run winding, and you saw it in the previous clip, when it was a bad cap, it went up to 53, right? 59, 53, 54, and it just got stuck, and then boom, the thermal overload switch opened, right? But when the capacitor is good, it is normal for that run winding current to go up, but then it comes down pretty fast. But how high it goes up, and then when it comes down, when it goes up and it goes up really high, it tells you why did it have to go up that high to then get the compressor to turn on. Because typically when it was working, when it was on with the good cap, as you saw in the previous clip, that was about 4 amps. That was about 4 amps. But let's say when we just turn it on, which we're going to turn it on right now, let's say it goes up to like 15 or 20, and then it comes down to 4. That makes sense. But what if it goes to 100 or 120 amps and then it drops down to 4? Something's going on. Why is it needing that much inrush current, saturated current, to then kind of get going if my capacitor is good? So that's just another indication of what's going on with the compressor. So keep an eye on this one right here. Okay, I'm going to go ahead and call for cooling. I want you to keep an eye on that and see the inrush current. And it's going to be in a split second. So you got to do it. You got to check it out pretty fast. Okay. So you saw that it was about, I was able to see about 165, 160. Why did it have to pull that much up, that much? And it still turned on. Don't get me wrong. Look, it's good. 3.6, 4, and 4, close to 4 on each windings. But why did it have to pull that much to then, pull that much to initially start it when the capacitor is healthy? So sure, when the cap is kind of bad, you'll see that. But when the capacitor is good and it pulls that much saturated current, inrush current, even though it drops down to 4, something could possibly be going on internally with the windings of the compressor. So that's another little thing you could check by checking saturated and inrush current on your run winding. And one thing you can also do is by checking the amp draw on one of the legs coming in. So this is a single phase 208 volt system. So you got 2 hot legs and a ground. So isn't it true though, when you think about it, all the loads, right? All the loads, condenser fan motor, your indoor motor, your compressor, your thermostat, your transformer, your contactor coil, all that, you can add it up basically by checking one leg, one hot leg. And so the one that I would check though would be the one going to my common on this side. So if I were to follow this black wire, it's gonna go, let's see if I can trace it here. It's gonna go to right here. Yeah, it's a mess right there. It's a jungle. We gotta clean this up. But it goes right here. You see, so that black wire right there, right? So once that gets pushed in, boom, it completes the circuit with a bunch of loads. I'm gonna check that black wire, right? So I'm gonna go ahead and call for cooling, right? And I'm gonna just check this wire, and it should give me pretty much about the current of all the components when I add them up. So obviously it's gonna be a pretty big amount when it comes to current, right? So we're gonna check this one here, right? It doesn't matter if it's this side or this side. So let's go ahead and call for cooling. Okay, give it a second. All right. Now I'm gonna check the amp draw, right? Amp draw. Okay, and it doesn't matter if it's on this side of the cable or on this side. And of course, if you're working on older systems, be careful it doesn't have a nick. If you have copper exposed and you touch that, you're gonna get hurt. So be careful with that. But you see, I'm getting a sum of different loads. So I think the compressor was at 4 point something. My condenser fan motor was at 0.6. And my indoor motor was at 1.8. It kind of makes sense. I'm close to 7, right? So it's giving me all the loads. So by checking that one leg, the one that goes to common, by checking that one leg, it basically is adding up all my loads, how much current it's all pulling. And so this is why it's important when you're sizing the equipment, the thickness of the wire, right? The lower the number, the thicker it is. That unit here, it says you're gonna have something called max breaker size. If it says 50 or 60, you gotta put the wire according to that amp rating, right? So that's important too, right? If you go to a job and you know it's gonna pull 30 amps, you're gonna put in the 30 amp breaker, you better put in a 10 gauge wire, not a 12 gauge. So there's different codes for different cities and different things that you're working on, but I just wanted to show you how you can check amp draw by just checking one leg. It gives you the amp draw of all the loads of the system. So I hope that this 3-part video series was able to help you understand how an electrical circuit works. Do you remember the 3 that we went over? One is potential difference, which is your voltage. The second one is checking current, right, through amp draw. And the third one is resistance by ohming it out. And we only went over 3. There's a lot more symbols, but just understanding those 3 that we went over can make you into a good service technician. And the reality is that an electrical circuit is not going to change anytime soon. You need 3 things to a circuit: a load, a path for your current to travel, which is your wires, your copper, and potential difference, your voltage. Understanding that, how an electrical circuit works, understanding how to use a meter, understanding where voltage is getting stuck. Is it a load? Is it a compressor? Is it a component that's going bad? Is it just that maybe power is not getting there? Is it a contactor coil? Different things. Just with that knowledge and with that meter and learning how to use it, because you gotta learn how to use a tool too. But just by doing those 2 things can make you into a good technician. And when it comes to troubleshooting and diagnosing, it's gonna make it a lot easier when you're out in the field. And of course, the safety is important. You can't be too afraid of electricity. You can't be too overconfident. It's gotta be in the middle, a balance. Some techs like to use gloves. Other techs like to use boots, or maybe different measures to prevent getting shocked. And yes, absolutely, do not get shocked. Be safe, because you want to make it home to your family. Yeah, there's so much to electricity, and it's interesting how electricity makes air conditioning systems work. I'm always in awe how it does that. But just going back to the point, okay? By using the tool and learning how to use this tool, whether you're checking voltage, resistance, or current, your amp draw, and that knowledge on where to check it in the system, those 2 things can help you become an amazing service technician. And there's always room for improvement for everyone. So I hope that you're able to benefit from this 3-part video series, and be safe out there.